Welcome, everyone. I'm Santosh Raikar, and today we're going to explore a fundamental truth in industrial operations. Plants rarely fail out of nowhere. Through When the Plant Tried to Warn Us, we will look at 5 global stories that highlight 11 reliability disciplines, all anchored by a single, vital operating principle. Before we dive into the cases, let's define our core challenge. A plant doesn't just break, it gives us signals. The disaster happens in the reliability gap, that space where a warning signal fails to trigger a decision, and that decision fails to turn into completed work. Our goal is to close that gap. Our journey spans the globe, from the chemical tanks of India and the fuel depots of the UK to the gas plants of Australia, the nuclear reactors of Japan, and the refineries of the US. While the equipment and regulations differ, the management challenge is identical. We must convert weak signals into controlled, verified action. To understand these events, we use the reliability operating chain. Every failure we'll discuss crossed these 5 gates. A signal occurred. Its meaning was interpreted, the risk was assessed, work was assigned, and finally, the proof of restoration was verified. Failure accelerates when we assume a gate is closed without actually verifying it. Let's look at our first case, Visakhapatnam, India in 2020. This story reminds us that even when a plant is silent and production is paused, the hazards within remain very much alive. During a lockdown, the plant stopped, but the styrene inventory stayed in the tanks. Because the normal routines were interrupted, the critical temperature and inhibitor controls drifted. As a seasoned professional, I've learned that preservation isn't just a paperwork exercise. It is an active operating mode that requires constant vigilance. The engineering reveal here is simple. Stored chemicals are active assets. Even in a shutdown, your asset strategy must continue covering refrigeration, recirculation, and alarm integrity. If you stop monitoring the age and health of your inventory, you lose control of the chemistry. So, what can you do Monday morning? Start by creating preservation plans for any extended outage. Treat your cooling systems as safety critical and audit your dormant inventories. Ask yourself, which idle asset in our facility is silently accumulating risk right now? Our second case takes us to Buncefield in the UK. Here, the tank was full, but the system was effectively blind. It's a classic example of protection existing on paper but failing in the field. During a routine fuel transfer, the level monitoring failed, and then the independent high protection failed to trigger. This led to a massive overflow and a devastating vapor cloud explosion. The lesson is clear. 2 instruments are not 2 barriers unless their failure modes are truly independent. The engineering truth is that a safeguard is only real when the entire loop is proven. You need the sensor to detect, the logic to interpret, and the final valve to actually stop the flow. Testing must recreate the actual demand on the whole system, not just a single component. On Monday, I checked that you're proof testing complete protective loops. Verify the bypass and override controls, and rank any overdue safety work by its potential consequence. Can every high trip in your plant actually stop the process today if it had to? In Longford, Australia, the loss wasn't just mechanical, it was intellectual. When a process upset occurred, it became a high-stakes test of organizational knowledge that the team wasn't prepared for. When a hot oil pump tripped, it caused a temperature collapse that the operators hadn't been trained to handle. Because the diagnosis lagged, an exchanger ruptured, cutting off gas to the entire state. The pump trip was just an event. The lack of knowledge turned it into a disaster. We must treat knowledge as a safety-critical asset. A competent team needs to be able to answer 4 questions under pressure. What changed? What is the consequence? How much time do we have? And most importantly, what is the safe, stabilized state? This Monday, focus on training for the consequences of failure, not just normal operations. Run abnormal situation drills and capture the tribal knowledge of your experts before they retire. If a critical pump trips tonight, does your team know exactly what to do 30 minutes later? The Fukushima disaster in Japan provides a sobering lesson on redundancy. They had backup systems, but those systems shared the same fatal weakness. Remember, redundancy without independence is just repetition. The reactors shut down safely after the earthquake, but the tsunami flooded the site, disabling both the primary and backup power systems. Because they shared a common vulnerability to flooding, the backups were useless. A safety layer is only as strong as its independence from the hazard it's protecting against. The engineering reveal here is to test the hazard, not just the machine. Don't just check if the generator runs. Ask if the flood can reach it. Do redundant cables share the same room? Can your people physically reach the equipment in a real emergency? Monday's task is to map common cause vulnerabilities. Look for ways to physically separate your power and controls. We must be deliberate in funding protection for these low-frequency but high-consequence events. What single event could defeat all of your backups at once? Our final case is Tesoro Anacortes in the US. This involves hidden damage in steel that was thought to be in a safe zone. It represents a significant challenge to our inspection confidence. Over years, microscopic hydrogen attack damage accumulated in heat exchanger. Standard operating curves suggested the equipment was safe and the damage was nearly impossible to detect with standard inspections. When a rupture happened during a startup, 7 workers lost their lives. We cannot rely solely on inspection when the damage is invisible. The engineering reveal here is that inspectability is a design requirement. A reliable decision requires looking at actual operating history and having specialists review damage mechanisms. If there is uncertainty that inspection can't resolve, you must consider a material upgrade or redesign. On Monday, verify your operating envelopes and challenge the capability, not just the completion of your inspections. If you can't reliably find the damage, you must ask, should we be redesigning this asset instead of just watching it? If we synthesize these 5 cases, we see a common architecture of failure. It starts with the equipment condition, moves through incomplete technical safeguards, fails within the work management system, and is ultimately shaped by leadership decisions. The impact eventually crosses the plant boundary into the community. To combat this, we use the Maintenologist learning architecture. This system connects governance, strategy, execution, and verification. It's only when these 11 disciplines reinforce one another that we truly have a reliable operating system. Each of the stories we've discussed today activates different parts of this system. Whether it's the work management gaps in Visag or the mechanical integrity challenges at Tesoro, these disciplines provide the tools to address the specific vulnerabilities we've identified. We can turn these stories into action with a 90-day plan. Spend the first month finding latent risks like dormant inventories. In the second month, strengthen your barriers with drills and proof tests. Finally, in the third month, close the loop by executing priority work and verifying the results. Here are 5 questions for your Monday morning. What is operating outside its design? Which protection is unproven? What does the shift not understand? What common vulnerabilities exist? And where are we asking too much of our inspections? In closing, reliability is simply the discipline of turning weak signals into verified work before disaster writes the lesson for us. The plant is always talking. What is your plan trying to tell you today? Thank you. For those who wish to dig deeper into the technical reports and investigation findings for each of these 5 incidents, I have provided the primary sources and links here. The full details are also available in the speaker notes. Finally, I would like to acknowledge the sources of the visuals used in this presentation. All images are used responsibly under their respective licenses to ensure clarity and educational accuracy. Thank you for your time and your commitment to reliability.